Okay. We're ready to start. So just an obvious announcement is that next week is a midterm, right? And a week after that is a spring break, which is good. Midterm is less exciting, but unavoidable. So midterm is on Thursday, right? Everyone is on board with this? Okay, on Tuesday we will do recap. Recap means I will try to highlight the most important things which we covered in the first half of the semester. It's also a chance for you to ask questions. So essentially, like, it's better instead of me kind of rushing through the slides, answering specific questions. So if you have some, just come in and just like get ready and ask them. And I think like the general rule of thumb is that if you don't understand something, most likely half of the class doesn't either. So, you know, like there are 2% of people who understand most of the stuff, and there is a huge pile of people who are like exactly like you. So don't be shy asking questions. And people who are top and bottom 10%, don't be shy either.
No,
Yeah, they're there. Like, just let me show you. And thank you for reminding me. I already forgot about it. Speak up. Say again. Yeah. So essentially, here on the website, I think there are two ways to, like, first of all, there is this link at the bottom, and I will make sure that it shows up here as well.
isn't that just fine?
No, it's a mix of both, but maybe not all the years. I'll try to edit this page, right? So that's one way to get to like all the exams which we had almost since this class existed. So again, are there what? Some of them don't have solutions. Some of them, and I will try to look it up as well. There were people who were solving them online and posting solutions. That's also fine. There was a repo. I will try to figure out it for you, but like, get ready that not everything is solved, but it's okay. I mean, if it's super confusing, ask on Piazza, and I will try to make sure that I can answer. I'll answer. But specifically to take a look at the last year's exam, I think you can go here, like previous years, and I think we post them here. Usually we do like midterm, so no link for whatever reason, but there should be a link, so I will try to fix it and make sure that. And here, like for the final, there is a exam and a solution. So essentially the same should be there for midterm. Maybe I just missed it. If you go one more year backwards, 2024, old website, but there will be supposedly midterm. Again, no, but I'll try to fix these links for you, but just keep pinging me. I most likely will forget, but I'll try. So we're not trying to hide them or anything, just like general sloppiness. Yeah, so look through the previous years to make sure that you understand what kind of flavor of questions we're asking. But this year, the rules are different. So we used to allow everything on the exam besides internet search. And this year, you only can bring printed material. Any questions? So start early. That's my advice as well. Just make sure that you get into the kind of into that flow of understanding what kind of questions might be asked and be ready. They do repeat. Like, I mean, there is only so much questions I can ask, but general kind of gist of those questions repeat. Not necessarily. So if you okay, let me just go to one of those exams, but we can discuss it on like, for example, here 2023, like we usually give you enough context so you can answer. Like if there is a question about the source code, Like in theory, I mean, the expectation is that you were reading the source code, which we covered in class, and you understand this source code. And the question itself does not require like additional reading of the source code. So this is probably a bad example, but I don't know which one. But essentially, we give you enough source code to provide an answer. So that's typically not a problem, right? And so, by the way, here probably, okay, I don't know, like exams are all over the. So you don't have to print it, but I recommend printing it just, maybe not even for the midterm, but just for final. Just final. The final exam will be asking more like cross-cutting questions. I might ask like, you acquire a certain log and then you do a context switch. And it seems that you never release this log. So why? And how does it work? Why it's not a dead log? And I mean, it's in the book and it's supposedly you were already assigned to read about it, but maybe you missed. And then during the exam, at least you can catch up. Makes sense? Anything? Okay, so we'll do the recap and I will try solving maybe last year's midterm on Tuesday just to show you what I expect is, and I will give you example solutions and stuff like that, right? But historically exams are like not super dumb, let's put it this way. So like just take a look, and it's not super hard, but it's not super easy either. And okay, sure. So we're ready for that, right? So that's essentially suddenly the attention, the focus, your focus suddenly at 100% once in a while. What else? Oh, good. So we're ready to go back to the lecture. Okay, so last time we ran out of time, and it's kind of worth recapping a little bit because it's just like, again, this page table management is at the very heart of operating system kernel. Arguably, Linux paging and virtual memory subsystem is the hardest subsystem in the Linux kernel. Like there are separate books just about memory management in Linux, and there are good books actually. And it makes sense to kind of understand how this is done. The moment you understand this, I kind of argue that everything gets a little easier in the class. And like this is maybe one of the most, like maybe the context, which is equally kind of tricky, but everything else is a little simple. Okay, so what I wanted to show you here, hopefully my pen connects in a second. Pen complains that there is no battery. Okay, so what we were doing last time, remember we said, okay, our super goal is to create a new page table. This new page table, in contrast to the one which we had in the past, will be a page table which maps just this region of kernel memory, which is above 8 terabytes. And how we gonna go about mapping or creating this page table is we're gonna take all available physical memory starting from 0 and going up to the special constant in the x86 kernel, which is called fistop, and we're gonna map everything with an 8 terabyte shift. So the physical address 0 shows up at virtual address 8 terabytes. I'll connect the pen, which is running out of battery. I hope I have a cable. That's the cable. And essentially we said, okay, sure, we're going to take a look at in details at the implementation of those functions. Essentially saying that, okay, like what is the function which takes a virtual address as an input, for example, this virtual address here, and walks the page table, allocates intermediate leaves, like if this is PML 4, will allocate all other PML levels, and eventually adds this physical address here to this very last leaf entry, right? So this is the function which we were looking at, right? And this is essentially the way to construct a page table. And there was a little bit of like infrastructure involved here. So we said, look, in reality, we gonna map not just a single region, but 4 different regions. And it will be 1, 2, 3, and 4. And the reasons for that is that permissions for those regions are different. So this region of the IO space will be mapped as read-write. The kernel read-only section and read-only data will be mapped as read-only, which prevents us, if we accidentally have a stray pointer which points into the kernel, and we're adding a new system call to x86, which will be one of the homeworks, and suddenly start overriding the kernel text, the bugs, the ways you crash after that will be so like spectacular that you will be hard time debugging them. But if it's a read-only and you're trying to write, you immediately get a page fault and maybe you can catch the bug a lot early. In a real production kernel, it's also done for security reasons. So you cannot like easily override if you found an exploit in a kernel, like a bug in a kernel, you cannot easily change the logic of a kernel. Then we're gonna map this one as read-write. Then ironically or surprisingly, we say, look, there is a region of potentially available physical memory, which x86 will just ignore. It will only work up until fizstop, but that's simplification just because x86 does not query the platform about all available physical memory. And we'll also have this one slightly different region, which is also similar to this IO space here, but it lives at the very end of the 4 gigabyte address space. Like it's like this address is 4 gigabytes, and it just leaves down from it. And we will map it at the very top of the 64-bit address space, right? So essentially right here, right? And so this is a slightly different shift, but okay, sure, that's a nice thing, right? So this is what we were doing, and we said, okay, so how is this function which maps this page table looks like? And we said, okay, sure, like logically, what you're going to be doing is that you take two addresses, virtual and physical. You take this virtual address and split it into like traditional 9 top bits, 9, 9, and 9 bits. And you say, look, and they all will control the indices in the intermediate page table levels. And so obviously you first allocate PML4, since you already have memory allocator. And I mean, I was kind of like, when I was talking about this memory allocator, I was saying, it's kind of like not a real allocator. But in practice, what's important here is that you actually can allocate anything from this memory allocator. The only restriction is the max size of an object which it allocates is 4 kilobyte. But if you want to build like a linked list of tiny data structures, sure, just use this kalloc and allocate something like 64 bytes. Of course, underneath it will allocate the object or for k, which means that you're wasting a ton of memory. But like how many objects do you really need for like maybe in a small kernel? Like maybe you need 100, so it's like just 100 multiplied by 4 kilobytes. Not a huge number, honestly. So what it means is that really it's kind of a dynamic allocator. It's just a very simple one. And if you like, maybe we'll come back to later in the class to how and discuss how we can improve it. But this is really like kind of like, if you think of malloc, which you always use in C, malloc is more involved. So it has like more ways to allocate smaller chunks of memory, but this kalloc is not too far off. So just make sure that you understand that this is the memory allocator which you typically see. Just inside malloc, instead of one linked list which manages objects of 4 kilobytes, like in our allocator, malloc will have like an array of pointers to lists of different sizes. Like, and the smallest size will be, let's say, 64 bytes, and that's the smallest unit of allocation. The next size will be, let's say, a list of 128 bytes, and so on. And you say, look, I want to allocate like 47 bytes. You round up to the next available power of 2, you get 64 bytes, and you just go to that list. But like you can see that there is like similarity between these two allocators, right? Pages, yeah, chunks, yeah. So in our allocator, we said, okay, for simplicity, it's a good homework. Actually, maybe I will ask you to do this, like improve extend x86 kernel memory allocator with full support of like malloc style. We can come back. That's a good idea. Okay, cool. So we allocate this object, which is a page, and of course, we are so careful that this is actually like 4K aligned, because if it's not aligned, nothing will work, but it's 4K aligned. And then you go and like take this 9 bits and you go into this PML4 level, you check this entry in the PML4 level and you check whether it points to something else or not. If it's not, you go and allocate this next level, right? And you say, look, what about the next one? You say, you take this 9 bits, you check the entry here, you say nothing is allocated, so you again allocate the next level, take this 9 bits, look at the entry here, say, okay, sure, is this allocated? Obviously, the first time nothing will be allocated. And then the last 9 bits, you pick an entry here, and you say, sure, and this entry will be specifically pointing here, right? That's the whole logic of this function. Very, very easy, right? But let's build it. And I said, okay, sure, let's like spend a little bit of time and understand how this function works. Just for the sake of, if you want to write, you will be writing this code in homework 3, like immediately, and potentially in some other homeworks in the future, right? Okay, sure. So we are in the main function here. We're calling this kv malloc function, which allocates a kernel page table. And we'll see this function multiple times later in this class. So it's worth spending time. What this function will do is that, say, I will internally call this function setup kvm. It will return me a pointer to the page table, right? Which we're going to create. And eventually we will switch with this function switch kvm, which will reload CR3 with the value physical address of this page table. Okay, sure. And we say, look, okay, like, let's take a look what's inside this setup kvm. Again, the call stack is here for your kind of convenience. And we say, okay, so very first thing which we're doing, we're allocating the PML4 level, right? Because we say, like, we're building a new page table on this function. So we definitely need PML4 level. And this comes from our memory allocator, right? Sure, that's easy. And after that, we said, okay, sure, since we are mapping these 4 different regions, we have an array of which is called kernel map with some number of elements, specifically 4. We iterate through this array. Each of this array has the start virtual address where we start mapping, the size, the physical start of the physical address, and what's important is permissions. Like I was saying, that the regions are read-only, read-write, read-write, read-only for the kernel, read-only section on data, read-only text on data, and read-write, and then another read-write for the bias, right? Question.
But the reason why the kernel map so the reason why the kernel map has 4 elements because there's the or
No. Wait. Okay, great question. So the reason we have 4 regions of memory, because we say that we observe that in our physical address chunk, which we want to deal with, I mean, everything is about physical memory, right? At some point, you have to manage it, right? And you say, look, I will be creating multiple address spaces. So, like, if this is your first page table, the first time you create a new process, like process 0 or process 1, you again will be creating a new address space, a new page table. That's why we will be reusing this function. And you say, look, we make an observation that our physical memory is split in 4 different regions. The IO space is mapped read-write because it has write permissions. Then the region right above it, starting from first megabyte, where we read where we loaded the kernel, should be mapped read-only because it's a text section of the kernel, and we don't want it to be overwritten. And on top of this text section, there is a read-only data section of the kernel. And if you're super careful about reading through this slide, I actually give you hints here. So it's text and read-only data here, right? And above it, we have kernel read-write data section. So we're going to map this region as read-write up until fizstop, right? And then there is a chunk of unused physical address space. We simply don't use anything up until this IO space, which again, if we want to write something like, I forget exactly which device uses this IO space in x86, because x86 doesn't have many. So maybe their IDE device, which is a disk device, IDE, uses this one, or SATA. Essentially, this is also mapped as read-write. So, and if you write into this range of address space of addresses, instead of reaching this physical memory, because it doesn't even exist, your DRAMs, they only cover physical memory up until here. It's just that the memory controller, which is attached to the CPU, pretends like it exists, and it sends it over the PCI bus to whatever devices are attached to those addresses. Question?
That unused space.
this, yeah, what in x86 it's never used. Unless you say, look, I know that my machine has 512 megabytes of physical memory, and then you adjust fstop to match this number. So it's simplification here. So just on a real system, which you boot on a real hardware, you will somewhere early on boot, you will query the BIOS, and because BIOS already knows because it participated in the boot protocol, ACPI, I don't really know the details. I always have it like, I always have a high level interface to this BIOS querying to BIOS. And essentially BIOS tells you, okay, I have 512. And then instead of a fixed fstop compile time constant, you say, look, I'm gonna map everything from here up to my available physical memory. That's like a normal kernel, like Linux. In practice, it's more complicated. Typically, there will be gaps in physical memory as well. And so it will return you some kind of an array of data structures saying that this is the physical memory, there is a gap, this is another one. And it's fine, you just like deal with it. No, it happens just because of how machines work. There might be gaps. So don't get super surprised about it.
Okay, so do all the processes get their virtual memory mapped into the free memory?
Do all the processes and the CPUs? Yeah. Yeah.
Those pages, do those get mapped inside the free memory spot of the kernel read-write data, or do
Yeah.
they go to that?
Yeah, and I will see it. Yeah, I wanted to see if I have a slide about it. Yeah, so, okay, how to better explain it? The short answer is yes. Maybe I have a slide somewhere here. Let's just go and figure it out here. Yeah, so, I mean, this is slightly incorrect because instead of this one, we should really put something like a fstop here. And it's like 8 terabytes plus fstop, and there will be a gap, and there will be this IO space region. This will be the address space of each process in a system. So like process like 1, which will be init, process 2, which will be shell, all will have identical memory layout above the 8 terabytes. So the kernel part of the address space will always be the same for them. So more specifically, it will look something like this. So all of these pages will be mapped to the same, like these are 2 processes. The lower part of the address space will obviously differ, right? Because you will put like shell here, you will put something like init here, right? But the upper part will always be mapping the same physical memory with this 8 terabyte shift. You will see it in a second. We haven't discussed it yet. And the reason is that all the processes in the system, conceptually, if you think about it, they share a single kernel, right? So you do a system call, and we'll come back to system calls. So for example, in a shell, you invoke a system call, you jump into the kernel, you start executing something in the kernel, running in those virtual pages, and imagine you do something like yield, meaning that saying, shell says, okay, I don't want to run anymore because I'm waiting for something or I'm done. And so I'm yielding the CPU, and you will do a context switch, meaning that you switch from this page table to this page table, but your instruction pointer, it's like switch is really reloading CR3, like move into CR3 register, right? And so you suddenly running on a different address space, you ran on this page table, now you're running on this one, but your instruction pointer stays here, right? And the fact that those are the same helps you to like, without too much trouble, say, look, I did my context switch, and I will exit and start running in it, right? You will see it later, but yes, you share a single kernel. And in order to share, you always map the same physical memory into the upper half of the address space, or not half a part.
Okay, so when we allocate memory for processes, are we using KAL?
Yeah, exactly.
Processes will run inside them.
Yeah. Exactly, because, okay, this is the good observation. So we say like, okay, sure, you made this nice diagram here, which kind of tries to explain a lot. And you said, okay, this like physical addresses, like you just said, okay, mapped with an 8 terabyte shift. But what about those pages? The pages which we say will be mapped here. So what we're going to do, we say, look, we say kalloc figures out a new available page on a list. Obviously, it's mapped, let's say, somewhere, I don't know, let's pick green one, somewhere here, right? Because it's a physical address. And you say, sure, I'm going to map this in this address space. I'm going to map this page one more time exactly at this address, which is like 4 kilobyte, let's say, right? So you allocated a physical page, you know that it's free, and you say, okay, I will use it for a process. I will map it at this, let's say 0, 4 kilobyte, and then you just load the text section of this process into this page.
And because it's on a different page table tree, because it's this process, it could have different permissions.
We'll talk about permissions, so this page here, this page is mapped with super user permissions, or let's say kernel permissions. But here we will map it with user permissions. Yeah, that's why I marked them as green here and yellow here. We will actually might even get to this today, but for sure next time. I will explain the permission model. Yeah. But it's the same page will be mapped twice, and you will see that there is a certain convenience in that. It's not always strictly required to do that, but let's do it this way in this kernel. Another question.
So the both processes have a user side and a kernel.
Correct.
And you map the kernel side both times, even though in theory, I imagine the kernel is kind of doing similar things in both processes, right?
Yeah, it's identical kernel. It's I mean, like literally, the virtual addresses, they're just a view of a physical memory, right? The view might be different, but you end up like seeing the data in the same physical page. So for example, the view of this page, this physical page has two mappings. So it's accessible from address 4 kilobyte and from some address in the kernel part, right? But it's literally contains the same data. The same for these pages, like this and this, it's like, let's say it's mapped to somewhere here, right? Yeah. And sure, like you obviously will, if you write here, next time you switch from one page table to another, like the same data will be available here just because it's the same data in physical addresses. Yeah, okay, so what's going on here is that, and again, there are different constructions possible, but what we said in this kernel, what we've done is the following. We said we were going to map all available memory, all available physical memory, which we have in a system like this with an 8 terabyte shift. Of course, if you want to start new processes, you have to figure out physical pages for them to keep their data, right? So naturally, like this is all available physical memory. So you have to pick one of those pages, right? There's no other way. And it's already mapped. It's mapped here, right? So, okay, sure. You say, look, I will write my exact system call, which will like read from, like it's running in the kernel, like you're doing a homework, parses the elf header reads it from this, parses the elf header, figures out the loadable sections like init, not init, text, says, okay, sure, I know that it could go here, right, in this page, right? And like you load it here, but you at the same time know that, okay, this page, since the process was like linked, for example, to run at address 0, should be mapped here in user address space, right? And when you start running user process, you set the instruction pointer around 0 and you start working, but it's the same page. It's just the same page mapped twice. You just access it. And there is some convenience that kernel can access user pages. But in our construction, we just said, okay, everything what's available, we'll map it in the kernel part of the address space. Roughly speaking, you can believe it for now, just say for convenience, but you will see why it works. Make sense? Okay, so sure. Any other questions about this confusing diagram? Yeah.
Process.
Correct. Okay, yeah, that's exactly like, what do you think if you invoke this function, whatever we were like, what is it? KV alloc, or even set up, like I know that you don't like remember the names yet, but so set up KVM. So let me just go to the source code really, like KV malloc, or like more specifically this function. If you invoke this function twice, set up KVM, right? And set up KVM, as we just discussed, what it did is just says, okay, look, I will like create you a new page table, which will map all this available memory with with those different regions, like with an 8 terabyte shift, plus this IO space going somewhere at the very top, right? And literally just does it, right? So you can invoke it twice. And the first time it will create this page table, invoke it twice, it will create yet another page table, which will be like different, because this physical pages will come from this free region, right? And they will be different, but like logically they will map the same addresses. So you can create multiple page tables, which will, if you give them the same virtual address as input, they will resolve it to the same physical address, let's say. Make sense? So you literally can invoke it multiple times. And this is what we're going to be doing. Every time we will be creating a new process, we will invoke this function that will give us a new page table. Does it make sense? Any other questions? All good? Okay, cool. So, sure. So the way we deviated into this discussion was that your classmate asked why we have a loop of 4 different, why are we looping 4 times? Why does the K map has 4 different entries? And the answer was that we have 4 different regions. Let me erase again, link like everything on this slide. So this is region number 1, region number 2, region number 3, and this is region number 4. And the way we define them is that we specifically said, okay, sure, this is K-map. This region number 1 starts at virtual address. We're going to map it at virtual address current base, which is 8 terabyte. It starts at physical start address 0. Physical end ends at extended memory. This is extended memory is 1 megabyte here, and the flags for mapping are writable, right? And the same for the other, like slightly different, but the same logic for the other 3 entries, right? Make sense? So we said, okay, we have a function which will map a continuous range of virtual addresses into a continuous range of physical addresses, because we observe that in our code that it's convenient, and we just will be reusing those functions, right? Make sense? And so what we do here is that we invoke this function map pages. We pass a pointer to the new page table, which we just allocated here. And we are looking at what's inside this map pages function right now. So this is the call stack. Main calls KV malloc calls setup KVM, setup KVM in a loop for 4 different entries calls map pages. Like map pages takes 2 arguments, virtual address and a physical address here. So we're rounding them down to the next pages. We get the 2 iterator variables A and last. And we essentially say, like, we're gonna run this loop until we break out of this loop when we reach A equals to last, right? And what we're gonna be doing in this loop is also reasonably straightforward. We say, look, in order to provide a mapping, we say, look, for this virtual address, in order to map it to this physical address, you have to walk this page table and essentially return the address of this. This is called page table entry, because all of them are page tables, right? And we say, like, if you have a pointer to this element in this array PML1, then you simply will assign physical address of your mapping plus the mapping flags here, right? So, like, if you have this function which returns you this PTE, which is a pointer to page table entry, then you simply do this assignment saying that you dereference the pointer with a star, you say physical address / or permissions or present bit, right? But you really need this function which returns you this PTE, right? And this is the core of it. So essentially, if you do this walk and you essentially say, look, I start from PML4 and I know that it's already allocated, you look at the next level, ask yourself a question, is it allocated? If not, you allocate it and you connect the previous level to this one, and you descend, allocate the next one, do the connection, descend until you get this PML1 level, and then you return a pointer to this PTE. Make sense? At this point, clear? Okay, sure. Okay, let's take a look at how we can implement this function, right? Walk PML4. And for sure, so as I was saying, what needs to happen inside, we just start looking at this level, take a look at this entry. If this link is present, we just descend. If not, we allocate the next one, and so on and so on. Let's take a look. So, okay, walk PML4 internally calls yet another helper function, which is called walk page level. And this walk page level just takes a starting entry. Like if you want to walk from PML4, you pass 4 here. If you want to walk from PML3, then you're going to pass 3 here. If you want to walk from level 2, then 2. And then if you want to walk just from 1, which essentially says, okay, here's PML1, here's the virtual address. So it will just take the lowest 9 bits of virtual address, returns you a pointer to this entry. So this will be your return value, right? So you're always returning this PTE pointer, right? Pointer to a cell, to one entry in one of the page table levels, right? So, okay, so how to write this function? Sure, so we say, that's very easy. So we're gonna write a switch statement based on this input argument level. And you say, look, sure, depending on which level we are trying to get to, we will use a slightly different, so because this is passed, so this is a pointer to just a node of a page table, and you say, look, you also give me a virtual address. So in order to resolve which entry you're talking about, you say, look, okay, sure, depending on the level, it will be either this 9 bits or this 9 bits or this 9 bits or this 9 bits, and there is also like an offset, right? So we will use a slightly different macro here, and those macros are not surprising. So you, like, for example, in this specific case, when you use, you say you take a virtual address, which is DA, you pass it into this macro, PML4 index or X will obviously return you this 9 bits, right? So this is exactly this macro. So you say the whole address is like the top 16 bits are ignored, then you have 9, 9, 9, 9, and then an offset within a page 12. So on this macro returns you index, or specifically these 9 bits, right? And the way you do it is that you say, look, I'm gonna shift it by PML4 shift, which just shifts by 9 plus 9 plus 9 plus 12. And you're gonna select those 9 bits. This is the mask which selects 9 bits, right? So reasonably easy, right? And those macros will be defined similarly for all like levels, right? Make sense? Okay, sure. The moment you got it, right? So you essentially said, okay, sure, I choose the entry, right? It can happen, right? Like if you are on level 1, you immediately return because you say, look, you were asking for this entry. I got you a pointer. It's a page table entry pointer. They call it like this, right? I can immediately return. However, if you're actually one level above, you say, look, I want to check if the next level is actually present, right? And you say, look, this is my code here. So you, in this entry, you check for the present bit, right? And again, if it's present, you just essentially say, look, if it's already present here, I will use this macros to get a virtual address of the next level. So roughly speaking, if you started from level 4, you located this entry, you say the present bit is set here. So which means that there is a physical address pointing to the next level. This is a physical address. And in fact, it's not just a physical address, it's the physical page number, because there will be some flags here in the bottom 12 bits, right? So you have to convert it to a virtual address. And this is exactly what you're doing here. So you're saying, sorry, I actually went. Great questions. Why do we have to go virtual? Tell me. Anyone? No, no, I don't. Anyone? Okay, why do you convert back to virtual? Yeah, but what's the inherent reason for why do you have to return virtual addresses? Correct. So because remember what we're gonna do with this. Let me just show you this code. In the end, we do this walk page table function, right? And we got a pointer. So if this pointer is a physical address, then you just in your kernel, you will go somewhere here. And if this entry is not present in a page table, well, you get a page fault. And so far, we're lucky. So because we have a page table which actually maps those addresses, but our goal is to like never map the lowest part of the virtual addresses. In fact, if you're doing this while executing a system call of some kind of a process, right? Then if you're running this like the function, something like whatever, walk page table level, and it returns you a pointer, and the pointer points to somewhere here, you actually can accidentally, and it's actually mapped, can accidentally overwrite bits of user memory, right? So you always shift back, because if you want to access them, if you want to put this address back into the page table or any other hardware register which expects physical address, then of course you will have to use a physical address. But if you want to access it, like dereference a pointer, you'll have to use a virtual address, right? Make sense? Good question, though. Like, it's important to understand those details, right? And the moment we do want to access it, right? So, and I forgot where I was. Here somewhere, right? So, so I was here and I was saying, okay, sure. It's sorry. Where is it going? Like, I got the entry. It's present. So I will do this conversion. So how to do this conversion? You say, look, I need to do, first of all, I take this page directory entry, let's say points to the next level. So it specifically points to this element in the array. You say, look, I take this, I will extract the address out of it. So it's like I use this two macros, one macro PTE to an address. And it's reasonably straightforward. You just simply like say, look, I have an entry, physical address is here. This is some flags here. So obviously this macro will just mask out those flags, turning them into zeros, right? And you will get the result, right? So this will become you just copy those bits and those you will mask with zeros, right? Make sense? So that's reasonably simple. And the second macro which you use is a P2V, and we already know how it works. It just like adds a shift. Right? Because you say, I want a virtual address, but we know that everything, at least in this address range, if you have a physical address which points, sorry, not here, somewhere here, you have a physical address which points here. If you add 8 terabytes, you will get a virtual address which will be pointing right where you want it, right? Make sense? And then you get a virtual address which points into this page which you're looking at, right? And to be more specific, if you got this entry, this will be a virtual address which will be looking at the next level. Make sense? Agree? Okay, sure. And there was a second case where we say, look, but what if this bit is not present? Then we say, look, well, sure, then we will go to the kalloc and allocate the next level. You can control this behavior with this additional allocate flag. And you say, like, if you don't pass, do not allocate, then sure, then yes, allocate. If the user says do not allocate, then this code just goes through, and then you like essentially like it's a different behavior. You expect a failure of this. You know that this is already allocated, right? But when you allocate this page, so it's reasonably easy. You say I allocated a page for the next level. I will set it with zeros just because I know that maybe this page was used for something else in the past. And in order to connect the two levels, right? So you say, look, if I got this entry, the next one was not present. I got this from kalloc, and kalloc returned me a virtual address, right? In order to connect them correctly for the hardware, you actually have to convert this virtual address into a physical address, and then you write this physical address into this entry of the page table. Make sense? And this is exactly what you're doing here. So you say, look, sure, we will use virtual to physical macro. This will produce a physical address. We set the present bit, you set the writable bit, and you set a user accessible bit. And you might be a little bit surprised because there is a comment here which says that permissions are overly generous. Why are you setting this a user accessible bit? But you can always restrict the access to this, to the page. Like here, you will not set the user bit, right, at the very last entry. Everything else is like user accessible. It's just a little bit easier to manage the code.
There's like laundry list of functions that we call. How often do we have to go through this entire process? Is that every time you want to access a new like memory address, you have to start from there? Do you start from like set up KVM or like how many of these would you have to repeat every time you try to access them?
Hold on. That's a good question as well, but you probably need to rephrase a little bit. So I'll give an answer and then you reiterate and ask again. What I'm saying is that this function, setup KVM, will give you a page table, a brand new page table, which will be empty. Besides that, it maps physical memory from 0 to fistop to virtual addresses starting from 8 terabyte to whatever, 8 terabyte plus fistop. And this tiny little region, which is IO space, which is mapped somewhere here as well, right? Otherwise, it's empty. And this is the pointer, which essentially points to this page table, right? This is actually a local, this is a global variable. Yeah, this specifically, in this specific invocation, it's a global variable.
So that's the kernel's page table group, like the pointer to the kernel's page table group.
Correct. But this function is generic, and you will see that this function will be invoked multiple times. And the question is like, how often do you need to create a new page table which maps the kernel part of the address space? So can you answer this? How often? Or anyone in the class?
Process.
I agree.
Needs a new page table tree.
Correct.
Kernel in the same spot every time.
Correct. So every time we will be correct. So every time we will be creating a new process, there will be a process data structure. Inside it, it will have a pointer to a page table. And every time you create a new process, you say, look, a new process will need to have a new, brand new user part of the address space. And it will need to have the same old kernel part of the address space. But you will be calling this function every time you will creating a new process. Because each new process will have a new page table, and one way to create a new page table is to call this function because it pre-populates the kernel part of the address space with the addresses we want.
Kernel space can map the same thing.
Correct. Correct. And that's a great optimization. So what you're saying is that process 1 should have maybe a unique PML4, and process 2 will have a unique PML4. Just because their user parts will be starting somewhere here, right, at the very entry 0, because we said that the user starts at 0. And this points to like their private tree, which maps the user part of the address space, right? Because this is private, right? So this is different between each process, right? But this entry can point to the same kind of like page table which maps the kernel tree. Agree with this? So this is shared and those are private. That's the observation you make. And this is how it's done in real operating systems like Linux, but x86 just makes the simplification just not to confuse you too much. And they say, look, forget about this sharing. We always create a new. But that's a great observation. Make sense? Yeah. We're almost there, don't you worry. 10. It's important to understand it because, okay, the whole core of like building an operating system is to figure out the layout of virtual and physical address spaces. The moment you do this, you're lucky. Everything else is a lot simpler. Okay, so sure. So we say we're in this function. There are two cases. Either it already exists or we allocated a new one. But in the end of the day, we connected them. We made a connection between the two levels saying that this pointer, let me erase it again. This pointer connects to the next level. Maybe we just allocated it. And what we're doing next, because our end goal in this function, do you remember? Our end goal is to get to this pointer. This is the end PTE pointer we want, because this is where we want to write the physical address, the address of this page, which will contain like the mapping, right? So our end goal is to descend, unless we're on level 1, we want to descend. And on level 1, as I was showing you, we just actually simply return here. But on all other levels, we fall through into this code. And what we're doing here is that we actually descend in the same function with the, with the new level, the same virtual address, the same alloc flag, but we're subtracting level by 1. Make sense? So that allows you to reuse the same logic, right? But overall, it's not like a rocket science, right? Like and I hope that after listening to me for like an hour or maybe like hour and a half, including class time, you will be able to read through this code and answer the questions and build a similar function for your own like homework and stuff like that, right? Okay, so in the end, what we achieved, we essentially, we descended, and at some point you were descending through this one, but at some point we will reach the end of it, and we will essentially we'll get this one, like we will return from this function, and we'll get this pointer, right? And here, let's just to solidify our understanding, let's quickly do a poll and try to answer. Yeah, wait, sorry. Stay with us. What I wanted to say here, like the poll simply uses one of those addresses, and I'm asking, what is that we are returning? Like, let me remind you, like, okay, sure. I just got confused about, yeah. The question, okay. Yeah. Good question. Returning from what? Remember, the whole goal, we were in map pages, iterating virtual addresses one by one in the increments of page size, right? We have this function, walk PML4, which returns us this pointer, PT, page table entry pointer, right? And I'm asking on this diagram, where does this pointer point to?
Or you mentioned the global variable pointed to by CR3. And we use that to kind of insert the kernel memory we get into each of the processes memory map. Right?
Okay, no, I actually don't mind walking, like looking at this again. So the end goal is to, like, what we're doing here, sorry, where are we? There are too many slides. So we have this map pages function, right? We are running inside setup KVM. we allocated a root of the new page table, and we're running in a loop, mapping 4 different regions into this page table, PML4, right? And the way we constructed this map pages function is that we say, look, you're going to provide a start virtual address and a start physical address, and you're going to loop iterating in the increments of 4 kilobytes, essentially mapping like a page by page. So if you want to map like one page here, we'll map it here, then the next page, then the next page, right? And you're saying, I have this little wonderful function, walk PML4, which essentially what it does, it says, okay, I'll start with the pointer to PML4, and I will create a pass through this tree, and essentially using these different indices, right? And what I'm asking here is, what is this function returning? Like essentially, if you call this walk PML4, right, what kind of pointer it returns? The source code, like this one. Walk yeah, sure. Just walk real quick. Where is it called? Like it's called from map pages here. And just to make it more exciting is that it's not too far off from what I will ask on the exam. Okay, do we have an answer? That's are we ready? Actually, the distribution is scary at the moment. Reconsider. Unless my diagram is wrong, which is also possible. So like this is the function, right? Let's take a look again at the question, like what is it I'm asking? Maybe I'm wrong. No, you're right. Yeah, less scary. Sorry, less scary. It just I made a mistake. Yeah, for sure. I should do this. Do we still have? Yeah, sure. Yeah, less scary. Okay, but some people believe that it's 1. So why do we believe 1? And some people believe it's 5. So I just wanted to clarify that for everyone. When we say, wait, sorry, what's this? Wrong color. Unreadable color. Let's make it readable. So when we call this function walk PML4, we're starting from a pointer to this page, right? And we're taking a virtual address, and we're splitting this virtual address. And the split will define the pass through this tree. But the end result of this function is this pointer, which will, in the end, we want to do like a mapping of this virtual address to a physical address. And in order to do this mapping, you have to write something right here, right? Because this is the actual page, right? And this physical address is combined with this offset, which goes in here, right? So the entry which you're getting is which one? You're getting this one. Make sense? And so like specifically, if I erase everything on this slide, you will just write the physical address right here, right? And you write the flags somewhere here, right? Make sense? So this is the page table. So this is PML4, this is PML3, this is PML2, and this is PML1, and this is the actual page which is mapped, right? So on this diagram, like essentially this, like, okay, which one is better? Do I have something good? Yeah. This is the virtual address of a page. This is the physical address of the page. This P will be essentially written at the very last level of a page table. So somewhere here. And that's why we need a pointer to this entry, PT, right? Make sense? Okay, sure. So I'll close the poll. Any questions? Okay, question. Yeah, sorry. No, like the walk page table with the walk PML4 returns a pointer to this one. Yeah, it's important to understand that like those nodes of the page tables, think of them as arrays, right? And you want to update an entry in the array, and this entry is that one. So this is what you want to update, and you need a pointer to this entry, PTE. When you dereference a pointer with a star, you will be able writing specifically this memory, right? And the pointer which you were going to write there, physical address, will be this 40 bits, which will be pointing to this one. Make sense? Okay, let's see. People did catch up almost. Okay, sure, me deactivate. Okay, but are we clear on this, right? So we spent like a ton of time on this function. We got the pool. We returned essentially, yeah, we return a pointer from this function to this one. And the way we return it, like just to emphasize, I will ask you maybe in a quiz homework, like which line of code returns this pointer? And who can tell me which line of code returns this pointer? Where is it? Which one? Hint is it? It's on this slide. 1752, right? Correct. So this is where you return. You reach the level 1. Your level is case number 1. And you essentially, this line returns it, right? Makes sense? But other than that, like if you don't reach this level, you keep recursing, right? Okay, good. So at this point, again, we're coming back to this function just for a second, but we're almost done with it. Like the whole point, like we looked at this function. The moment you got the PTE, your job is done because you already have a physical address. You check whether it's present. If suddenly it's not present, you just say, wow. Oh, actually, if it's already present, it means that it's already mapped. Then at this point, you screwed and you say, okay, I'm panicking, like something wrong is going on because it shouldn't be mapped. And after that, you say, look, I will place the physical address, which I'm mapping, permissions, and a present bit. And if you reach the last address, you started from this to you breaking out of the loop. If not, you increment by 4 kilobytes and do the same, like iterate here, walk the next virtual address, get the next PTE, update it with the next physical address, and so on, right? So the function map pages, maps a continuous range of virtual address to continuous range of physical address, and you're just iterating through this range, right? But it's kind of like, again, if you look at it like 3 times, it looks like super easy at this point. Like, wow, like why did you even waste our time? We probably should have figured it ourselves, right? But still. Okay, the moment you're done with this function, you get a new page table, kernel PML4. You say it's time to switch to this page table. So you call the switch function. The switch function itself says, okay, very easy. I will take a virtual address of this page table root, convert it to a physical address, and we'll load it into CR3. CR3 uses assembly, inline assembly, to just say like, because C doesn't allow you to say move something into CR3 register, right? So you have to like use a little bit of inline assembly. And as a result of this, what we did is that, remember, we started on a page table, which is called entry PML4. It only had like 3 leaves. This was mapping 1 gigabit of memory, 1 gigabyte, and this one mapping 1 gigabyte of virtual memory as well. And we said, okay, and CR3 was pointing to this page table. Now we said, okay, sure, we allocated a new one, kernel PML4. This is a more real page table, which has all this like additional levels, which maps like the same regions, or like not the same, but similar regions, because we map up until fiztop plus another region on the top. But CR3 is pointing to this new page table. And this one we will never use again. We only used it for the boot, for booting on the CPU and initializing the memory allocation and everything. Make sense? Okay, we achieved quite a goal. So at this point, we are done with initializing kernel memory. And since we still have like 10 minutes, let's start the next thing. And our next thing is actually start talking about interrupts. So just like a brief kind of like outline what's coming, right? So we were right here. And to some degree, the question is like, okay, we're inside the main function. We got the kernel page table. I set 3 dots here. Intuitively, what should happen here at the very end of the main function?
The main function, we would be handing over control to the shell that would be confirmed to things.
Correct. So we will create init process, and init process will create a shell. And you start essentially right before the very end of the main function, we will create these 2 processes. And at the very end of the main function, we'll start running a scheduler. And essentially the scheduler says, okay, I will pick the next available process from this available process list, and I will switch. And at this point, you start running user code, right? Up until there, you will be running like main, right? And then the scheduler says, okay, I'm going to switch to this process. And at this point, it will start running the very first instruction of the init process, right? In fact, actually, shell will not be created. Init will fork and exec into the shell, right? Question?
Yeah, so the other stuff, so we're not using segments. The segment descriptor. We're not using position independent code.
Will not, yeah.
It says disabled. So when we want to process, we won't have to relocate stuff except for.
Yeah, so x86 inside exec will be using a very simple elf loader, which is like almost verbatim what you write in homework, just like iterating over loadable sections. The expectation is that they all are ready to run at address 0, kind of statically linked to run at address 0, no dynamic linking, nothing, no position independent code. Just loaded at address 0, which means that like if you have a page table, map address 0, map the next page, load the text section, start running, right? Create a stack. Yeah, not in x86, but hopefully by the end of this class, each of you will say, it's like, I can do this, like for an extra credit, I will relocate anything within like 2 hours. So it's not a problem. One correction, we will be using segmentation just because you cannot even enable paging without segmentation. I will come back to it in a second. But my question is like, what has to happen in between these two? What else is left? We have kernel memory allocation. So we can do kalloc. That's great, which means that we can build page tables, which is also great. What do you think is still missing? A couple of other interesting parts. We have to cover them. After that, we go into creating new process. Correct. So you correctly observe the fact that in order to like run the scheduler, you probably want to have a ability to preempt a running process, right? Meaning that if init starts running, at some point, we don't trust init to call back into the kernel and say yield. Maybe it has an infinite loop. So in order to preempt init, you say, look, I want to handle interrupts, like a timer interrupt. So you actually have to set up logic for handling external interrupts, like from a timer or a disk, some other devices like console, right? That's what x86 supports, like UART, meaning keyboard and serial line. And okay, sure. So you say, look, I need to have interrupts. And interrupts are also used in some or abused in a different way. Interrupts also allow you to implement a controlled transition between user code and a kernel code. Think of it as a TSA checkpoint at the airport. They're not going to let you to enter the airplane just like without passing through TSA, right? And so interrupts allow you to like switch privilege levels from user to kernel in such a way that the kernel can apply those checks and say that you're entering through a correct entry point and you're passing correct arguments, right? And sure, so interrupts are also used for that, or historically were used for that. So on modern machines, there are faster ways to implement interrupts, like there are newer instructions which allow you to do it faster, but x86 still uses interrupts, right? Which is fine, like it's nice kind of introduction, right? And more or less, like modular, like initialization of other subsystems, like file system, but initialization is easy. One major piece which is missing is interrupts, and another major piece which is kind of missing, but it's very simple, is bootstrapping other CPUs. So we will, the moment we understand how we handle interrupts, we will figure out how we can wake up other CPUs. Like now we're like running on one physical CPU, but we say, look, but really we have more. Maybe we have a system with 4 physical CPUs, and they're just sleeping, kind of waiting for us. But at the end of main, we will send them magical interrupts saying, okay, because we already know how to initialize the interrupts, and we wake them up and enter a simpler but similar main function on all of those other CPUs. And on all of them, we will be running essentially a scheduling loop, which will access the global queue of processes in the system. And essentially a shell can run on CPU 0 for a while, then be context switched, then other physical CPU will pick it up, and physical CPU number 2, for example, run it for a while. And this is how the system is running. So essentially this is multi-processing. Make sense? Okay, cool. So we kind of understand that what's coming. So we're not too far off. And then the moment we have all these mechanisms, we will take a look at how we implement system calls, essentially how to build something like exec or fork. And the moment we have this, we will take a look at how to implement context switch. Essentially logic of switching from running one process to another, a little tricky, but not super hard. And after that, we're almost complete. We say, look, we build a kernel, it can start a new process, it knows how to do syscalls, knows how to process a timer interrupt, on a timer interrupt to switch from one process to another. And the only missing part will be something like a file system and device drivers. And x86 doesn't really build a lot of device drivers, but we will take a look at the file system. So that's essentially the overview of the second half of the semester. And sure, so any questions right now? Good. You guys know that the poll is not coming. Okay, let me ask you this. What do we know about interrupts and why do we need them? Okay, sure. Let's take this. Oh, sorry, I missed it. Correct. So interrupts can be split roughly in 2 broad categories, synchronous and asynchronous. So asynchronous are coming from external physical devices like a timer. You're executing your code, everything is happy, and a timer says, okay, well, sorry, I want to execute an interrupt here. And that's asynchronous because like it's like really some other piece of physical hardware send it like a signal to a CPU saying, okay, like stop doing what you're doing, switch to this interrupt. And it's like example of a timer. And synchronous interrupts, again, can be of 2 flavors. One, close to what you actually described, which is kind of like abnormal conditions. So for example, you're dividing by 0. And at this point you say, look, well, moving forward doesn't make sense because no matter what you compute after that, it will be a wrong result. I mean, you might have a theory what is correct after dividing by 0. It's like, it's okay, sure, like you can recover maybe. But typically CPU says, okay, it's an exception and you can handle it. You can terminate a process at this point. Or if it's a page fault, like you said, you can say like it's instead of like terminating a process, you know that this page maybe is shared and it was never yet mapped, but you lazily mapping the pages, or maybe you took this page to disk and you just have to bring it back and reestablish the mapping, right? Okay, nice. So yeah, we'll take a look at those synchronous exceptions, like critical conditions like page fault, or maybe protection violations, which you typically observe as seg faults, right? when your program is crashing. We already talked about asynchronous sources like a timer, right? And what is the last bit which I was mentioning before? System calls, exactly. So exceptions, syscalls, both the synchronous and asynchronous are exceptions like or interrupts from devices like a timer or can be a disk. x86 has it because you say, I issue a write or I issue a read. I'm not gonna, like in our boot code, we're just looping, waiting for the disk to finish the write. Here, instead of looping and wasting like 20 million cycles for the disk to finish, we'll just move on, do something else, and then wait for the disk to send us an interrupt saying, okay, I'm done, right? Okay, let me stop here. And when we come back, after the spring break, actually, we will continue with the interrupts.
Thank you.
Yeah.